In this video, we will discuss about depth-first search, and we will finish by showing a pseudocode of the depth-first search implementation of CP. The important question that we will answer in this video is, what does a search tree look like? How do we define the search tree? How do we explore it? And we will see that there are different strategies to explore the search tree. And finally, how do we terminate the search? We might terminate once we have found one feasible solution, or for some problems, it's important to discover all the solutions. In constraint programming, the nodes of the search tree represent the computational state. It means the state of the problem, so the constraints. The constraint might also contain some state, and the variables and the domain after having computed the fixed point. And to create branches from a search node, we will partition the search space. And to do that, we will act on the variables. We will pick one variable, split the domain in different parts so that we have restricted subproblems that we can recursively explore. Let's take one example here for the n queens. As you can see here at the root node, we've got the initial domains, and then we will pick one variable, in this case q0, and we will split it in two different parts by choosing one value, and we will assign this variable to this value to the left, and to the right we will remove this value from the domain of q0. And we do that recursively by restricting the problems, and every time we restrict the problem, the fixed point computation will be able to remove more infeasible values. And eventually, if you are lucky, you will discover a search node where all the variables are assigned and no constraint is violated, which means that it's a solution. Let's define it more formally. What are the different strategies that you might have for splitting the domain of the variables? In option 1, you pick one variable x, and you pick one value and you assign it to the left to this value v, and you remove it to the right. You remove this value to the right. A different strategy is to split the domain in two, and so you will pick the mid value of the domain, the median value, for instance. On the left, you will restrict the domain of x to be less or equal to this median value, and to the right, you say it's strictly larger. And these two first options are binary strategies. Every node will be split in two different branches. Another strategy that would also be a valid one is to consider n-ary labeling. So given a domain size of n plus 1, you will create n plus 1 sub-nodes, n plus 1 children, and every children will be restricted to the value that is assigned to this variable. So the leftmost branch will contain the value 0 only in the domain of x. The second branch will assign this variable to 1, and so on until the value n, okay, for each of the n values inside the domain of this variable. So, more formally, what is important is that given a constraint satisfaction problem as this one, a branching strategy is a procedure that's able to decompose, and it will generate k different constraints. Okay, they might be 2, for instance, for binary split, or it can be n for domains of size n, if you consider n-ary labeling. So, but in general, we say that you will be able to generate k plus 1, in that case k plus 1, different constraints. Okay, and these are the branching constraints. And the important thing with these constraints is that the union of the solution in all the restricted subproblems is equal to the initial solution. Okay, it means that we do not discard any solution. And another important requirements for this branching constraints is that the intersection of the solution is completely empty for any pair of these constraints. Okay, and this is really this is more optimization requirements. We want to be efficient. We don't want to explore redundant search spaces when we split the problem into parts. So this is a little bit less formal, but the requirement is that you cannot lose solution when you decompose, and you should not repeat solution when you solve each problem independently. And as you can be convinced, I hope, is that the three strategies that we have just seen before satisfy these three requirements. So, branching strategies is a recursive process. At every node, you will explore again the branching algorithm that is able to generate for you the branching constraints. Okay, and it has a huge impact on the shape and the size of the search tree. We already mentioned that in a previous video, but again, the variable that you will choose and the value that you decide to assign to the leftmost branch and so on has a huge impact, potential impact on the size of the search tree that you will explore. So it's really important to implement carefully these branching decisions. Okay, so we want to be also efficient when we implement this branching constraint exploration. So in general, we decompose the problem as follows. First, we pick one variable, and then we choose the values on the branch that we want to assign this variable to, and the order in which we will enumerate this constraint. Okay, this is the leftmost constraint. Okay, so if you pick this one, we will have C0, then C1, and then CK. And as we will explore the search tree using a depth-first search strategy, this order matters a lot as well. Okay. What we consider as a static variable ordering is the one that consists in picking the first unbound variable and assigning it to the minimum of its value, minimum of its domain to the left. Okay, this is called the static variable ordering. This is a good strategy to start with, but in general, this is not the most efficient one for solving problems. What if the variables are already all bound? In that case, the branching will simply return true to say that there is nothing else to do, and just to notify the solver that this should be considered as a feasible solution to the problem. Okay, we call that the unary branching. So how do we explore the search tree? So the order in which the nodes will be examined is really the search tree strategy exploration, and the one that we use, and that's mainly for efficiency and for ease of implementation reasons, is the depth-first search. The depth-first search has very important properties. The amount of space that it requires is proportional to the depth. So if you go from the root node to the current node in the depth-first search, the size that you will require is proportional to the depth of the current node. Okay, and the only state that you need to store is all the ancestor nodes previous to the node that you are currently visiting. Okay, and so it's very easy to implement, and this is also a chronological search. Okay, and so the backtracking strategy is also more easy in case if you have state restoration, and we will see that a little bit later. How do we terminate the search tree now? Once we have, for instance, one feasible solution, we could terminate the search tree, or we could also decide to backtrack when one of the domain becomes empty. So if one of the variables has an empty domain, we should backtrack. And finally, the recursive case is when you don't have detected a non-feasible situation, and you have some of the domains with a domain size which is larger than 2, which means that the variable is not yet bound. In that case, you need to recursively search and call your branching strategy. You can decide to go for one solution. Okay, in that case, you stop as soon as you have found one feasible solution. Or another strategy, which is the one used in optimization, is to discover all the feasible solutions. This is the template, so the pseudocode of the depth-first search strategy. In input, you have the CSP, so the domains. You've got the domains here, the variables, the domains, and all the constraints. And as the result, this algorithm is producing for you all the feasible solutions. Okay? So here, what you do is that you propagate. Okay, this is a fixed point. This is a fixed point propagation. You call the fixed point. You get as output the new domain that we indicate here with a star. So this is the new domain. In case the product size of the domains is equal to 0, it means that you have detected an infeasibility. Okay, there is a domain wipeout. This is also the name that we use to say that one of the domain becomes empty. You return the empty set to say that below this CSP, there is no solution. Okay, there is no solution in this CSP. In case the product size of the domains is equal to 1, you return the solution, okay? You return the solution that you just found. And otherwise, this is the recursive. You branch, which means that you produce all the branching constraints that you have here, and you will recursively call the CSP, the CSP search recursively on the new problem that is restricted by adding this constraint, this branching constraint CI. And you will collect, since this is returning the set of solutions for these restricted subproblems, you will collect all the solutions here, okay? And which means that by relying on this specification, you can convince yourself that overall this algorithm is correct as well. This is an abstract algorithm. This is just a template. And as you can see, this is a template that can be implemented in very different ways. And one important thing that you might specify for this algorithm is this branching algorithm that you can specify and that you can customize for specific subproblems. Okay, so this is the empty domain detection, this is the solution detection, this is the branching, and this is the recursive call here that you have. In the next video, we will show how to implement for specific subproblem this branching recursion procedure.